Hi, Assalamualaikum and a very good morning. Now we are still on chapter 1 reaction kinetic, but currently we are on the subtopic of 1.1 reaction rate, which is part 2 of the video. So if you haven't watched part 1, please watch it now. Okay, in this video we're going to learn what is meant by rate law, order of reaction, and also have to learn to relate rate law with respect to the order of the reaction. Also in part 2, we're going to learn how to determine the order of the reaction involving a single reactant using the initial rate method and the unit of rate constant. But for the other part, which is labeled in green, we're going to learn that in part 3. Alright? So, what is rate law? Rate law or rate equation is basically an equation that relates the rate of the reaction to the rate constant K and the concentration of the reactant raised to some powers. Okay, easier to visualize this, let us consider the equation to be AA plus BB going to CC plus DT. So if you were to write the rate law, it's going to be rate is directly proportional to the reactant, and we have reactant A and B respectively. So if you were to write the rate law, it's going to be rate equal to K, which is rate constant, and the concentration AX and concentration of By, where X is the order of reaction with respect to A and Y is the order of reaction with respect to B. And for determine the order of the reaction, we have to add up X and Y in order to determine the overall order of the reaction. So if X is equal to 1 and Y is equal to 2, means that we know that the total or the overall order of the reaction going to be 1 plus 2 equal to 3. And K here refers to the rate constant, where you know that the value of X and Y basically can be determined experimentally. Okay? So order of a reaction is usually defined in terms of the reactant's concentration, but the order of the reaction is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. So as what you can see here, the reaction of fluorine gas with 2 Cl2O2 will produce 2 FClO2. Here, many of you will be tempted to write the rate equation to be the rate law or rate equation to be F2 to the power of 1 and ClO2 to the power of 2. However, this is not necessarily true because the order of the reaction, which is 1 and 2 here, is not related to the stoichiometric coefficient. As to be in this case, you can see here basically ClO2 in the rate law going to be 1, but in the chemical equation, it's have 2 here. Alright, so therefore, in order for us to determine what is the exact value of X and Y, we have to determine it experimentally, or we can use that from the experimental data. Alright, so let's say we have the reaction between oxygen gas and the nitrogen monoxide to get 2 mole of nitrogen dioxide, and this is the experimental data. So we done the experiment 1, 2, and 3 respectively. And we know that the rate law going to be rate K, which is the rate constant, the concentration of the reactant O2 to the power of M, which is the unknown, and O to the power of N, which is also the unknown. So in order to determine the order of the reaction, we have to compare 2 experiments in which the concentration of one reactant varies, satu berubah, satu maintain, and the concentration of the other reactant remains constant. So, in order for you to understand this better, let's look at the example. Okay? So, to find the rate reaction order with respect to oxygen, we compare experiment 2 and experiment 1 respectively, because we have 3 experiments, right? But we focus on these 2 because in which the NO concentration is held constant. Maksudnya NO concentration itu adalah sama, and the concentration of the oxygen is double. As what you can see here, there is a difference here. So what you're going to do first, you initially will divide the rate of the experiment 2 divided by rate of the experiment 1, where rate of experiment 2 is equal to K O2. 2 here refers to the experiment 2, and O N of the experiment 2. And same goes to the experiment 1 here. Alright? And as what you can see here, basically they are the similar term, because K and K can be cancelled out, and oxygen, concentration of the oxygen can also be the concentration of NO can be cancelled out, because it's 1.3 times 10 to the power of negative 2. Same goes to here. So you can cancel out that one and also cancel out this one. So what's left is the concentration of the oxygen, where this term here will also refer to this thing. So we can just directly relate the rate equal to this thing. Okay, now we can, in order to find M, we can substitute the rate given in the experiment. For experiment 2, the initial rate of experiment 2 is 6.4 times 10 to the power of negative 3. Meanwhile, the rate of the experiment 1 is 3.2 times 10 to the power of negative 3. So 6.4 and divided by 3.21. And the concentration of O2 of the experiment 2 is 2.2. Meanwhile, for experiment 1 is 1.1. So once we do the math, we will get 2 to the power of 1, which is 2, and 2 to the power of M. And this is the rule of indices. So the base here is the same. So you will directly can know that M is equal to 1. Okay? So we can say that the reaction is first order with respect to oxygen, because M refers to the oxygen. So the conclusion here is very, very important. Do not leave the answer hanging like this. Once you find the answer, you have to make the conclusion here, where the reaction is first order with respect to oxygen, where first refer to 1. Now we already know M. So the next step is we have to find the N, the unknown N here. So we use the similar technique. So in order to find the reaction order with respect to NO, we compare experiment 3 with experiment 1, in which oxygen here is the one to be held constant. It's the same, right? So we can assume it can be cancelled out. And N2 is the one being doubled here. Okay? So actually, it doesn't matter whether it's doubled or tripled. As long as one is being constant, you can find the unknown of the other. Alright? So the same thing as before, rate of experiment 3 of this equation and rate of experiment 1. So K can be cancelled out, and as what you can see here, oxygen can be cancelled out as well. So you know that rate 3 is equal to rate 1, refers to the concentration of NO of the experiment 3 and NO of the experiment 1. So we can substitute the value, where rate 3, experiment 3 is 12.8 here, and rate 1 is 3.21 times 10 to the power of negative 3 here. And the concentration of NO for experiment 3 is 2.6 here, and the concentration of experiment 1 of NO is 1.3 here. So just substitute that in. So once you do the math, you will get here, you will get 4, and here you will get 2 to the power of N. And as you know that 4 is a 2 to the power of 2, and hence you can say that 2 is equal to N. So you know that N will gonna equal to 2. And as I mentioned, do not leave the answer hanging to be like this. You have to make the conclusion where the reaction is second order with respect to NO. Alright, so from the previous slide, you know that M is equal to 1, and now you get N is equal to 2. So you can put that again in the rate law, where rate law that we have just constructed at the earlier slide is rate is equal to K O2 to the power of M, and rate K O2 is equal to NO to the power of N. So M is equal to 1 and N is equal to 2. So we have to substitute it back again. Alright. Now we're going to relate the relationship between the order of the reaction to the rate of the reaction. So the order of the reaction that we will be usually dealing with is the zero order reaction, 0, 1, and 2. So zero order, first order, and second order. Now let us look into the zero order first. So if you were to consider the reaction of A going to product, we can write the red law to be K is equal to A to the power of X. If it is a zero order reaction, then X is equal to 0. Alright, so we can say that this reaction is zero order with respect to A, where X is equal to 0 here. So A to the power of 0 is equal to 1. So K multiplied by 1 is equal to K. So the conclusion that we can get is the rate is independent of A. So what we really mean by this was, whatever the value of A, but because of it is to the power of 0, it is still equal to 1. For example, 9 to the power of 0, if you put it in the calculator, it will still equal to 1. Or 1 times 10 to the power of 5 to the power of 0, we will still get 1. So what we can say about this was, in a zero order reaction, the rate is independent of A. Regardless the value of A, the rate will be equal to the rate constant. Alright? Now we're moving on the second one, which is X is equal to 1, which is the first order reaction. So let's say if we have A is equal to 1, we know that our rate is going to be 1K. However, if A is doubled from 1 to 2, we know that our rate going to be changing into 2K. Okay, so the conclusion that we can get from the first order reaction is, if the concentration of A is double, the rate of the reaction will also be double. Okay, so if A meningkat, concentration of A is meningkat, rate of the reaction will also be meningkat as well. Now let us look into the second order reaction if X is equal to 2. So rate is equal to Ka to the power of 2, and we know that this reaction is a second order with respect to A. So if you were to assume that the concentration of A is 1, the rate that we will get is 1K. And if you were to change the concentration from 1 to 2, we can see that the rate is now become 4K. And hence, we can say that if the concentration of A changes by X time, where here is double, which is 2 times, the rate of the reaction also changes by X squared time, where here 2 is equal to changing by 4 times. Alright, so in order to understand this better is to look at this summary. So for the zero order reaction, the concentration of the reactant varies, it does not give any impact on the rate. Okay, but for the first order reaction, if the concentration of reactant is double, the change in the rate will also be double. However, in the second order reaction, if the concentration is double, the change in the reactant gonna be increasing by 4 times. So it's basically refers to X, and the change in rate gonna be X squared. Here, if X, the change is gonna be X. Okay, so if this one is triple, the here will be triple. But here, if this one is triple, this one gonna be 3 to the power of 2, which is 9. Okay, so this is the best summary to look at it. Now let's look at an example. So the rate of a reaction increases 8-fold when the concentration of one reactant is doubled. Determine the order of the reaction with respect to that reactant. Okay, so the first thing that we need to do is the red law, where R is equal to K A to the power of unknown, where we choose alpha here. So from the question, it says that when A is double, or when the reactant is double, the rate increases by 8-fold. So rate increases by 8-fold, become 8R, and A here become 2A. Okay. So now we can rearrange the equation to be 2 to the power of alpha, k, and a to the power of alpha. And as what you can see here, k to the power of alpha basically refer to r. So we can change this one as r. And r here can be cancelled out. So we know that 8 is equal to the power of alpha. And 8 is basically 2 cubed. And 2 alpha is still 2 alpha. And hence we can say that alpha is equal to 3. Thus, the order of the reaction with respect to the reactant A is equal to 3. And this is how we can find the order of the reaction by relating it to the concentration and also the rate of the reaction. Alright, now moving on, we can also find the order of the reaction by determining the unit of the rate constant. Okay, for a zero order reaction, rate is equal to k to the power of 0, right? Where rate is equal to k. So you know that the unit of rate gonna be equal to the unit of k gonna be equal to the unit of rate. Where the unit of rate that we have learned in part 1 is equal to molar per second minus 1. Okay, so if the question gives you the reaction rate having a unit of ms minus 1, you will know that the reaction happens to be a zero order reaction. For this one, first order reaction, we can see that rate is equal to Ka to the power of 1. And hence, rate is divided by concentration. And as we know, rate will originally have the unit of ms minus 1, but now divided by molarity. So molarity and molarity can be cancelled out, and hence left with minus 1. Okay, so for the first order reaction, the rate constant K here have a unit of S minus 1. For the second order reaction, we know that the rate is equal to Ka to the power of 2. So rate is equal to A square. So for the unit of rate constant K is equal to ms minus 1 over m square. Okay, so we can cancel that out, and what's left is m minus 1 and s minus 1. Okay, to understand this better, look at the summary table here. So if the unit of K is ms minus 1, it is a zero order reaction. If s minus 1, it is first order. If m minus 1, s minus 1, it is a second order reaction. Alright, and this is very helpful for you in order to solve the problem regarding the reaction kinetics, because in some question they will ask the decomposition of hydrochloric acid, for example, has a rate constant of 1.3 times 10 to the power of s minus 1. So it doesn't mention whether it's first or second, but it gives the unit of the rate constant. So you know that if the unit of the rate constant is s minus 1, you know that it is a first order reaction. And this is how it can be really helpful. Okay, now let's look at an example. So the decomposition of N2O5 at 45 degrees Celsius is a first order reaction. So the chemical equation is given as 2N2O5 gas decomposes into 4NO2 plus oxygen gas. So we have to write the rate equation, or the other name is the rate law for this reaction. So we have to write rate is equal to K and to the power of multiplied by its concentration, which is concentration of the reactant N2O5 to the power of 2. Is it correct or wrong? Alright, so 2 here is wrong. We don't write the stoichiometry to the power of its stoichiometry. Instead, we have to write it in terms of the order of the reaction. So it's supposed to be rate is equal to Kn2O5 to the power of 1. Alright? So we really need to be careful on this part. Now, for part B, we have to calculate the rate constant K if the initial concentration of N2O5 is 1.5 times 10 to the power of negative 3 molar, at the rate decomposition of N2O5 is 8.6 times 10 to the power of negative 7. So we have the rate law and we need to find the K here. And N2O5 is given, which is 1.5 times 10 to the power of negative 3 molar. And the rate decomposition is also given, which is N2O5. But be careful, we have to find the rate of the reaction, not the rate of the decomposition. So we know that the decomposition of N2O5 is basically 8.6 times 10 to the power of negative 7, right? So as we do the rate of the differential equation, we know that rate is equal to negative 1 over 2 multiplied by this term. So we have to put in the value here, and therefore the rate of the reaction going to be 4.3 times 10 to the power of negative 7 molar per second. Now we already got the rate, and we can substitute the rate into the equation, and we can find K. So we can do that here, where K and the initial concentration of N2O5 is 1.5 times 10 to the power of negative 3, equal to the rate that we have just calculated. And by doing maths where we divide it, we will get K is equal to 2.87 times 10 to the power of negative 4 per second, which is S minus 1. And as what you can see here, the rate constant gives the value of S minus 1, which basically refers to the first order reaction, which is delta. Alright, I think that's all for this video. See you again some other time. Bye.